Last time on Chronolab, Max Planck rescued classical physics from the ultraviolet catastrophe with a bold mathematical assumption. Look at the high-frequency tail of this blackbody curve. To stop the classical prediction from flying off to infinity, Max Planck proposed a strict limit. The material inside the oven could only exchange energy in precise steps, related to frequency by his new rule, E equals h nu. That mathematical fix rescued the spectrum, but Planck applied it only to the physical matter of the oven walls. He assumed that once those material resonators emitted their discrete energy, the light smoothed back into a continuous, unbroken wave as it traveled through the vacuum of space. Albert Einstein noticed a tension in this compromise. Einstein suspected that Planck's equation was revealing something deeper. He asked whether the quantum belonged to the light itself. But you cannot simply look inside a light beam to see if it is made of independent pieces. Without a direct microscope, Einstein needed an indirect test. If light traveling through space behaved like a gas of independent particles, it would leave a highly specific statistical fingerprint in the mathematics. To find that fingerprint, we need to count hidden arrangements. We can look at a system and describe its overall visible condition, its macrostate. But beneath that visible surface is a microstate, the exact hidden arrangement of its individual parts. This animation shows how physicists manage those numbers. The total number of hidden arrangements is W. Because W grows so violently large, we pass it through a mathematical logarithm to compress it into a useful, slow-moving thermodynamic value known as entropy, or S. Entropy is a record of how many different microscopic ways a system can be scrambled internally while maintaining the exact same outward appearance. W represents the raw number of those possibilities. Einstein knew the entropy behavior for a gas of physical particles. His strategy was to calculate the entropy of high-frequency light and see if the math produced a match. To understand the mathematical pattern, consider this layout of 3 numbered rooms and 2 distinguishable cats. The black cat has 3 choices. The orange cat also has Brie. Because their decisions are independent, the possibilities multiply, giving 9 distinct hidden arrangements. If we expand the house to 6 rooms while keeping the same 2 cats, the arrangements multiply again. 6 times 6 gives 36. A pattern emerges. The total number of arrangements equals the volume of available rooms raised to the number of cats. W grows as volume raised to the power of n. A dilute gas follows this same logic. A fixed number of identical molecules explores a container. If you expand the container, the same individual objects simply gain more places to hide. This mathematical relationship is the hallmark of a system made of independent, countable pieces. Classical wave theory behaves differently. A wave is not a collection of objects moving through a void. We can picture its possible states using a vibrating string, where specific frequencies act as the system's available modes. This string supports 3 allowed standing wave shapes, or modes, below a chosen frequency limit. When you double the length of the string, you do not simply give the existing shapes more room, you create entirely new independent wave modes. The total energy can be shared among a larger list of frequencies. In this classical picture, the energy acts like a continuous fluid. It can be divided smoothly and poured in any proportion among this growing number of modes. A wave's possible arrangements are defined by modes that change with the size of the container. This contradicts the fixed scaling relationship found in a gas. Einstein applied this test to light. Using a rule for high-frequency radiation called the Wien limit, he isolated a narrow band of light, placed it in a volume, and calculated how its entropy changed as that volume expanded. The math produced a startling result. The entropy of the light scaled in the exact same pattern as a gas of independent molecules. In Einstein's calculation, the energy behaves like a group of localized points that move through the volume without ever splitting apart. By setting n equal to the energy divided by h nu, he could describe the light as a collection of independent, indivisible energy quanta. Calculations on paper are only half of the story. Einstein applied this model to a mystery at the heart of Philippe Lenard's laboratory, the photoelectric effect. Lenard was shining ultraviolet light onto metal to knock electrons loose. Classical theory predicted that a brighter wave would batter the metal with more force, ejecting the electrons with more kinetic energy. Trace these curves from Lenard's actual data. Brighter light released a massive flood of additional electrons, but they all hit the exact same energy limit. The intense wave failed to give any individual electron a harder punch than the weak one. Classical physics had reached an impasse. Existing theory offered no way to explain how a massive wave could impart the exact same energy to a particle as a dim, weak wave. If light arrives in discrete packets, the interaction follows a strict one-to-one energy budget. One incoming quantum, h nu, transfers its energy to exactly one electron. A portion of that energy breaks the electron out of the metal, and the remainder becomes its escaping energy. Making the light brighter doesn't make the individual packets hit harder, it simply delivers more of them. To increase the energy of the electrons, you must increase the frequency of the light itself, making each individual packet larger. This chart shows Einstein's bold quantitative prediction. If you plot the maximum kinetic energy of the electrons against the frequency of the incoming light, the data must form a perfectly straight line. Robert Millikan thought this light quantum idea was absurd. He spent 10 years trying to disprove it, only to verify that every single data point fell exactly on Einstein's predicted line. In 1905, Einstein published the paper that established the photoelectric equation and redefined the nature of light. Max Planck had used E equals h nu as a mathematical trick for how matter exchanges heat. Einstein gave it physical reality. The photon, a true quantum of light, had been discovered. Einstein had shown that the electromagnetic field travels through space as a stream of distinct, localized energy units. With the physical existence of quanta supported by data, the investigation turned to matter itself. Next, we follow a young researcher who applied these quantum rules to the internal structure of the atom.
In the next episode, we enter the atom, and classically, it is already doomed. A radical new idea will try to save it.